Hey guys, welcome to another video for chemistry. In this video, we're continuing our video playlist on covalent bonding. In this video, I'm going to be discussing single, double, and triple bonds and how that affects bonding strength and bond length. So let's go ahead and dive in. So there's three different types of bonds. So there's types of bonds and then bond order that we're going to discuss in this video. Bond order is the number of electron pairs being shared by any bonded atoms. So in other words, if I have a single bond, one bond, that's a bond order of 1. If I have a double bond, okay, with a sigma and a pi bond, that is a bond order of 2. And if I have a triple bond, which is three pairs being shared, that's a bond order of 3. Okay, so there's three different types of electrons, or different types of bonds, that we're going to discuss. The first being the single bond, the double bond, and then the triple bond. So let's talk about exactly what that means. So let's start off first with the single bond. So a single bond has a bond order of 1, as I mentioned before, the most common type of bond. Okay, and so here are two examples of that single bond. You have a diatomic molecule of hydrogen 2, and then you have another type of molecule of carbon and hydrogen. This is a very common one in organic matter. Okay, so those lines, those single lines, if you remember from a previous video, those single lines represent 2 electrons being shared from each element, and that forms a single bond, one single bond. Okay, so hydrogen will always have a single bond. If you think about the position of hydrogen, the oxidation number of hydrogen is a +1. So that gives you a hint as to how many bonds it could potentially make. And all elements, you can look at the oxidation numbers of every element, and that will give you a hint as to how many bonds it can make. Hydrogen being group 1 is oxidation number 1, so it can make one single bond max. So again, here's that diatomic molecule, or a diatomic molecule that we've mentioned before, oxygen 2, that is atmospheric oxygen. So when we say that you're breathing in oxygen, you're literally breathing in O2. You're never really breathing in an oxygen by itself. Well, you could actually. That's actually called a free radical, and those aren't necessarily good for you. So O2, let's take a look at that. Let's examine how exactly O2 bonds. And to do that, we're going to look at the meaning of a double bond. Okay, so double bond, you see 2 lines there representing 2 pairs. So that means there's 4 electrons that are being shared that form that double bond. Okay, so if I look at each oxygen by itself and I look at how many valence electrons it has, I know that each oxygen has 6 valence electrons, meaning that it needs 2 electrons to make a pseudo-noble gas. And again, recall the position of oxygen in the periodic table. Okay, it has 6 valence electrons. It has an oxidation number of -2, so that means that it can make a single bond, 2 single bonds, or 1 double bond. So for oxygen, atmospheric oxygen, let's look at how the mechanism behind how those electrons, or how this bond is formulated. So you see here that there's an unfilled valence shell. It has empty space that it wants to desperately fill. And luckily, the neighboring oxygen atom has electrons that it could use. So the shared electrons will fill the empty p orbitals of each oxygen. So one electron from one oxygen will be shared with another electron from another. So that's 4 electrons, 2 electrons from each oxygen that will end up getting shared, as signified here. So 2 electrons from each oxygen, and those 2 electrons will make 2 pairs, which means 4 electrons, okay, which will make a double bond. Okay, and I can signify that by my 2 double lines there. I have a sigma and a pi bond. All right, so let's look at how these bonds actually help satisfy that octet, the octet rule for each element. So as I'm analyzing the oxygen on the left, I notice that it has 2 unpaired electrons, so that's a total of 4. And then I look at the other electrons that are being shared, that also equals 4. So that gives that oxygen a total of 8 valence electrons, which gives it a pseudo-noble gas notation, which satisfies the octet rule for that oxygen. Now let's look at the oxygen on the right. you have the same thing. You have two unpaired electrons, 4 electrons in total, and then you also add the shared electrons from the other oxygen, and that gives it a total of 8. So in this case, you have each oxygen having 8 valence electrons and becoming stable. Okay. Now let's look at a triple bond. So for a triple bond, we're going to look at oxygen's neighbor, nitrogen. So 3 bonding pairs, 2 atoms sharing 6 electrons. 2 atoms sharing 6 electrons. This is going to be a bond order of 3, a triple bond. So this is atmospheric nitrogen now. So how does this happen? Let's look at the mechanism of how this happens. So you have 3 bonds, triple bond. So let me go back for a second there actually. So you have 1 sigma and you have 2 pi bonds, right? You're always going to have at least 1 sigma bond. So nitrogen has 5 valence electrons. So we want to analyze which electrons are going to end up being shared. And so those three electrons from each nitrogen will end up being shared. Okay, and again, that's my Lewis dot structure, and I can replace my dots with my triple bond, my triple lines. Okay, so now that we kind of have an understanding of what a single, double, and triple bond is and how that works, let's look at how that affects bond length. Okay, bond length, and what we mean by that is the distance between the nucleus of one atom to the nucleus of the other atom. So how does a single, double, or triple bond affect the bond length? So let's first analyze the bond length of a single bond, okay? A single pi bond. So to do that, I'm looking at hydrogen combined with 4 different other elements. I have fluorine, chlorine, bromine, and iodine. Let me go back to the positioning of the periodic table. I want you to see it how it looks on the periodic table because I want you to recall electronegativity and how I want you to see how this is going to play a role. Recall that fluorine is the most electronegative element on the periodic table, and as you go down, electronegativity decreases. Okay, so chlorine is very electronegative, but not as electronegative as fluorine. And then bromine is very electronegative, but not as electronegative as chlorine or fluorine, and so on and so forth. Okay, so electronegativity goes up as you go up the periodic table, and it goes down as you go down. So having that principle in mind, let's see how that affects the bond length. So all of these are sigma bonds, but just because they're all sigma bonds does not mean that they are identical. Okay, they actually differ in length. And these properties that we're discussing right now are actually what causes these particular molecules to have different characteristics. They behave differently in nature. They have different purposes in nature. Okay, so fluorine being the most electronegative element on the periodic table, look at the bond length. Okay, and the PM signifies picometers, right? So it's 92 picometers compared to chlorine, which is not as electronegative. So fluorine is super electronegative, super electron hungry. So it's going to hold on to those electrons really, really tight, and it's going to pull hydrogen a little bit closer, creating a shorter or the shortest bond length between hydrogen and any other halogen. So as you go down the line, okay, and this is the same order that's in the periodic table. As you go down the line, you notice that the bond length gets a little bit longer and a little bit longer, and that's because the elements, as you go down, are not as electronegative, so they don't hold that bond as strong. So not all single bonds are created equal. Not all of them have the same length, and not all of them have the same bond strength. Okay, and that's what we call bond energy. So in order to break up hydrogen and fluorine, look at the amount of energy it requires, 565 kilojoules per mole, compared to hydrogen and iodine at the bottom, which is 295. Okay, so the bond length, the fact that hydrogen and fluorine are so close together and bonded so strongly, it makes sense that it would require more energy to break that bond. You know, in class we talked about how, think about how easy it would be if you extended a hand to somebody and just shook their hand and your arm was completely straight out forward. How easy would it be to break that bond? Just pretty easy. Well, what if you were linked arm to arm, and what if you were like hugged, really close together? The breaking of each of those bonds, those hugs, would depend on how close the bond actually was. to the other person. And likewise, that principle is similar to how elements and the bond length or the strength of the bonds are based off of electronegativity of the two elements. Okay, so the more electronegative, the more bond energy and the shorter bond length. All right, so now let's look at the difference between, so we have three different bonds. We have carbon with oxygen, and they're different types of bonds, and that one of them is a single bond, one of them is a double, and one is a triple. And each of these different types of bonds is possible. Okay, well, in principle, anyways. If you look at the different bond lengths, carbon, the single bond with oxygen is 143 picometers, and the double bond in carbon and oxygen is 123, and the triple bond is 113. So what's the pattern that you see there? The more bonds there are, the shorter the length is. Okay, so picture shaking hands with one hand, shaking hands with two hands, and shaking hands with three hands. Well, we know that's not possible, but just consider the fact that the more bonds there are, okay, the tighter those elements are going to be held closer together, so the bond length will shorten as your bond number increases. Okay, and then as I look at the bond energy, same thing. So the triple bond is substantially stronger than the single bond at the top. So so for the single bond, it takes 358 kilojoules, whereas a triple bond takes 1070 kilojoules. So you can see that the strength progressively gets stronger by the bond type. And also, inversely, the length gets, so the stronger the bond, the shorter the length. Okay? So it's important to kind of see those patterns and recognize those patterns and understand why those patterns exist. Okay, so let's look at another example. You have nitrogen. You have a nitrogen with a single, nitrogen with a double, nitrogen with a triple. Now look at the bond lengths. The triple bond is much shorter than the single bond, and then the double bond is in between the two. So take a guess. Now you're not going to know offhand how much the bond strength is, but just take a guess as to which is going to be stronger. Okay, if you guess the triple bond, that is correct. And the weakest bond will be the single bond. Okay, substantially weaker, 160 compared to 945 kilojoules. All right, and so that pretty much sums up our covalent bonding and the types of bonds. So we had single, double, and triple, and we also discussed the bond lengths and how they differ from bond to bond, and the bond dissociation or the bond strength of each of these types. I hope this video helped. If you have any questions, we can discuss these in class, and good luck in your study.